Good afternoon, everyone. Am I audible? This is Professor Sandeep Ohol.
Yes, sir.
My voice is clear, na, Sudarshan?
Yes, sir. Your voice is clear, sir.
Yeah, yeah. Thank you. We'll wait. We will exactly start at 2 o'clock. Huh?
Okay, sir.
Hello, good afternoon.
Yeah, good afternoon, sir. Rebi sir, there is some background noise from you.
Hello, good afternoon, all. Can somebody
Yeah, good afternoon, sir.
respond if my voice is fine and I'm audible?
Yes, sir.
Good
You are
afternoon, sir. Your
audible.
voice is fine.
Yeah, good afternoon, sir. This is Professor Sandeep Pahol. Am I audible?
Yes, sir. Yes, sir. You are audible.
Am I audible?
Yes, sir. You are audible.
So,
Yes,
should I
Sandeep sir,
start,
you are audible.
Mayur sir, should I start?
I think he is yet to join. I think you can start. He is a bit in traveling.
Okay.
I'll connect with him. You can start meanwhile.
Yeah. Good afternoon, everyone. Dear participant, welcome to the second day of 2 weeks International Faculty Development Program on Robotic Vision using BOS, ROS, and machine learning. We have with us today our esteemed guest, and it's my privilege to introduce Sir in front of you. Uh, Professor Dr. Ribi Abraham Bobby is an assistant professor in Department of Mechanical Engineering and affiliated faculty at IDRP on Robotics and Mobility Systems at the Indian Institute of Technology, Jodhpur. His research focuses on robotics, computer vision, and human-machine interaction. He has authored numerous scientific articles in this field since 2011. He holds a BE from National Institute of Technology, Karnataka, and MS from the Indian Institute of Technology, Madras, and a PhD from Indian Institute of Technology, Delhi, all in mechanical engineering. Before his current position at IIT Jodhpur, he was a senior researcher at Innopolis University in Russia and an assistant professor at Indian Institute of Information Technology, Kottayam. He also previously held researcher and consultant role at IIT Delhi and IIT Madras, as well as engineer position at Sandvik Coromant. He has been involved in international collaborative projects, exchange programs with TU Munich, Germany, CNU, Korea, Waseda University, Japan, Innopolis University, Russia, etc. He is involved in multiple projects supported by Russian Science Fund, NRF, ICSSR, etc. as PI, co-PI, cumulatively worth more than 2 crore Indian national funds. Large number of bachelor students and 8 master students have completed their project under his supervision. Apart from academic commitments in teaching and research, he was actively involved in administration at IIT Jodhpur as coordinator IDRP Robotic and Mobility Systems, President Board of Co-Curricular Activities and Professor in charge non-faculty recruitment, and have been in program committee of various international conferences and is reviewer for numerous journals, conferences and grant proposals. So we have such an eminent personality today as our today's speaker. Welcome, sir, to this FDP, and session is yours. Thank you. Thank you very much.
Thank you, Professor Sandeep Ohol, for the kind introduction. I hope my voice is audible.
Yes, sir. Your
Your
voice
voice
is.
is audible, sir.
Okay. So, I think as per our schedule, we are supposed to start our session soon. So I will share my slide And please confirm if you are able to see my slide.
Yes, sir. Your slides are visible. Good to go, sir.
Okay, okay. Give me a few seconds so that I can start up.
Yes, sir.
Uh,
Yes.
yes, so I specifically thank the organizers for this opportunity, uh, for having me at this particular faculty development program at MIT Pune. So today's session, I would be focusing on the robotic vision aspect. And since that is closely connected with the topic which is uh, a focus of this FDP program, that is robotic vision using ROS and machine learning. So I will not be covering aspects of ROS, but rather I will be focusing on robotic vision aspects fully. So before I start, let me also set up some of my annotation systems. Maybe a few seconds I may take. Okay, anyway, let's start with the session. Uh, I am from IIT Jodhpur. So before I start, let me give a small introduction about IIT Jodhpur. IIT Jodhpur uh, has it had its inception in 2008. We have about 500 plus bachelor students intake every year, and then plus additionally masters and PhD students getting admitted. So our total student size would be almost 7,000 around, uh, considering all kind of students. So we have conventional departments like any standard institute, plus centers, schools, and some interdisciplinary programs like IDRP. And uh, if if time permits, you okay, might be when you are free, you may also watch this particular video in YouTube, which is called Pearl in the Desert. That is about IIT Jodhpur. So, so we are situated towards in Jodhpur, towards the entrance of the start of Thar Desert. So therefore, it is considered as like a pearl in the desert, but it's not like exactly desert. So you can see from the photo the bottom that it is also green. So currently we have like quite a bit of rains and all. So, so that is a brief introduction about my uh, uh, institute. So I thought, since it's my first session, I will start with basics of robots, and then slowly move on to the aspect of robot vision. Uh, and so, uh, when you look at the general definition of a robot, so it's normally called as a reprogrammable multi-purpose machine, which can actually move things like tools from one point to another. So this definition is based upon ISO standards, and on the bottom you see different kinds of robots. This is a quadruped robot. This is a bipedal humanoid robot. This is like an industrial robot, the most commonly found robot here. And lastly, we see this vacuum cleaner uh, robot, which all of them are falling in the category of robots. So the category definition of robots has become quite a big when compared to what was existing earlier. Uh, then when we look at the presence of robotic systems, the most common one is an industrial robot, and that was the third photo from the left. Uh, so as per ISO definition, it is automatically controlled, it is reprogrammable, it is multi-purpose, and it is a manipulator which is programmable in 3 or more axes. So it is nothing like a steel or a metallic kind of arm. So human have arms, so exactly the same replication, and that is used to uh, build that uh, example is used to build a robotic arm. Excuse me, am I audible?
Yes, sir.
Oh, okay. So I can continue from here, right?
Yes, sir.
Okay. So then there's this famous dialogue in one of the movies. Uh, I think the movie, it's like something like "Mera 10 kilo ka haath." So this is something like 100 kilo haath. So that means each of these robots will be having uh, like a very large mass, uh, and then it will have a particular payload, and payload will normally be attached at the end of the robot for all these kind of robots. So then while we were defining it, we were using the terms reprogrammable. So you have programmed motions and then auxiliary functions. So these programs or auxiliary functions can be changed without physical alteration. Just by changing the program, you can have a different kind of functionality. It is multi-purpose, that is, it can be used for a different application by just slightly changing the physical system. And what do you mean by physical alteration? Physical alteration means the mechanical system, that is mostly the end effector would be changed, and then it would be used for a new application. And what do you mean by axis? All those were part of important words which are part of the definition. Axes are directions along or about which the robot has independent motions. So it would be either linear or a rotary kind of axis. So what is the historical background behind such a robotic system? It is actually a fusion of two technologies, and which all are the two technologies? One is telemanipulator system and another is CNC system. So if somebody had the privilege of going to BRC Mumbai, there is a system something like this. This is like a telemanipulator system. So this is used to manipulate radioactive elements or objects or hot objects, etc. And then if you are from mechanical engineering or manufacturing background, you know CNC machines. And CNC machines, you could write code in G or M code, etc., and then make it do specific tasks one after the other. So telemanipulator had a human to control the manipulator, but CNC could be programmed. So So the programming aspect of CNC and this hand-like aspect of the telemanipulator system were combined together, and then that led to the development of industrial robots. So we have different kind of industrial robotic systems like Cartesian robots. We have SCARA robots. So this is like an example of a Cartesian robot. So there will be prismatic joints, or the joints which do translation, which allow the link to do translate along a particular axis along three Cartesian axis, Cartesian coordinate systems. And if it is SCARA robot, we have two parallel axes. So mostly it would be used to have motion along a particular plane, but then there is like motion outside of the plane using another particular axis. So this is common types of industrial robotic systems. And if you call anything and like an
Excuse me, sir. You went on to mute.
I'm sorry, till when did I go to mute? Can you
Just
please?
now, just now.
Sorry. My
Okay.
mistake, I would have. Yes. I'm not so used to Microsoft Teams. So therefore, if there
Okay.
is some issue, you please give me feedback so that I can
Yes,
adapt
sir. Yes,
accordingly.
sir.
No issues,
Yeah.
sir. Okay, sir.
Okay. So then additionally, you will also have parallel or delta robot. So it will have concurrent prismatic. So what I see here, what I show here is like a parallel robot. What is the difference here? The serial robot has a structure uh, like the chain, kinematic chain is like an open kind of chain. But if it is a parallel robot, it is like there is one connection here, another connection here, and the third connection here, and there is like an end effector which is used to orient it, which is oriented using this kind of connection, and the movement happens in this particular fashion. However, this is like it moves like this chain, open chain. This is like an open chain. Open chain orients the end effector at different locations. And you have a cylindrical robot whose axis form a cylindrical coordinate system. If it is Cartesian, the axis is along Cartesian coordinate system. If it is cylindrical, the axis is along a cylindrical coordinate system. And examples of usage of these systems are welding, painting, handling of metal castings, packaging, etc. Again, it can also be used for polishing, some grinding kind of applications, machine feeding, material handling, etc. So these are the applications for articulated robots. Parallel robots are used for picking, placing, uh, mainly in food and beverages industry, FMCG kind of industries, and then can also be used for assembly, some kind of handling, etc. And Cartesian robot can be used for material handling mostly and machine feeding, etc. And this also has most of these applications involve a larger workspace. So there are some traditional robot manufacturers, like you may know about this. One is KUKA, you have ABB, you have Fanuc, and then there are less common ones like Nachi, uh, Daihen, Epson, and this is actually a collaborative robot. So in India, we have some few companies like Adobe manufactures collaborative robot, Swaya Robotics manufacture collaborative robot, and then there are other company uh, in Bangalore. One other company also manufactures collaborative robots, but mostly industrial robots are manufactured outside. Earlier, TAL robot used to be there. That was in Pune. Perhaps someone would have had an experience of seeing that. That was like an industrial robot. But I think as long as like for some time it is not like it is being not being produced. The activities, production activities have been stopped. So why I'm talking all this is like if I look at the amount of installations of industrial robots, it is increasing from like if you look at 2018 to 2027 uh, till 23 as per the data you can during the COVID time there was like some saturation, then it increased, and then it is predicted that it will increase at this rate of 4% per annum. So this is there is a organization called International Federation for Robotics. They release these information statistics. And if you look at the worldwide installations, uh, most of the installations are happening in Asia. We see that China, Japan, Korea having large number of installations. We at India, we are also picking up in a big way. So, which says that in the future there is always possibility of a growth, and uh, uh, then in Asia there will be big market for industrial robotic systems. So now most of the industrial robotic systems have a very old kind of system, uh, and normally if you say that somebody is working like a robot, so what you mean to say is that that person is not applying his mind and is not using his brain and doing some productive kind of task. But right now, the focus on such system is on creating automated production within the concept of Industry 4.0 and then currently evolving Industry 5.0. We need systems which are interconnected. You need the robot connected to sensors and then connected to processors, and then the whole system can be automated, and then you can collect data from all the sources and then you can optimize the performance, and then you have this possibility of building digital twin. So if you have a robotic system, you can have models of the robotic system which is very similar, which will work exactly similar uh, within very close tolerance to the robotic system, uh, so which will help us to say that the performance will be within this particular limit, and you will also be able to uh, check the status of the particular system. And then there is this concept of uh, if you have heard about software as a service, so there is this perspective that you don't need to buy a software, you just take the service of the software. So something like that, there is a possibility of like getting the robot as a service rather than a product. And one of the major focus is on sense and respond, which we will again focus on, because we have to sense the external environment and then respond accordingly. So some of the most important and emerging aspects are these collaborative robots, application of artificial intelligence, and then using sensing and feedback. So these are like some aspects. You need energy efficient robots. You need robots to enable production. Many of the earlier production systems have been sent to more farther places because of financial viabilities. There will be possibility of bringing those production process back to this place where the main company is existing. Then we need robots which are easier to use. We need the possibility of refurbishing robots, and then AI and digital automation is something which is coming up in a big way, and therefore artificial intelligence and sensing is something which is of paramount importance. So now, while coming to collaborative robots, so the robots which we looked at earlier, there was no human that was present in the workspace. Now, when we have collaborative robots, human and robot will work together. So that means the workspace, workers can enter the workspace of the robot. You have sensors to detect human motion, and then the robot will work as per that particular sensing that has been obtained. Now, these collaborative robots are designed to work alongside humans, and then therefore it is called as cobots or collaborative robots. So it does not cause a harm or like an accident kind of situation when the worker comes in direct contact. So it has inherent possibility of controlling some level of force interaction between the human as well as the robotic system, etc. So that some damage to the human or even to the robotic systems can be avoided. So if you look at the level of collaboration and then the safety features that are required. Earlier, what we had is like very less collaboration. That means robot had a particular cell. You are not supposed to go inside the particular cell as per the robot safety considerations. Now, with collaborative applications, we can allow to remove that safety fencing around the robot. So the robot as well as worker can coexist without the safety barricade. Now, for this, you need a like more capabilities of the robotic system through sensing and suitable response. And then you had the possibility of sequential collaboration where the human does something, the robot does something. These are the areas where most of the collaborative uh, actions are happening. But what is more interesting and what is more like more people are working on is cooperation, where robot and worker work on the same work piece, uh, but like nobody controls the other person. But a more few like further requirement would be where the human can make a motion and ask the and the robot can become like compliant, and the robot can follow the particular motion of the human depending upon the kind of forces that the human exerts. So this is the highest level of collaboration that we have to focus on, but that also requires a higher level of safety consideration so that human does not get hurt. Now, the robotic systems, though they are moving to collaborative systems, etc., those are the more uh, interesting application of industrial robots. But in industries, what we are actually been obsessed about for so many years is this aspect called automation. So in one of the professors, that is Professor Kenneth Goldberg, so he was editor-in-chief of one of the IEEE journals, IEEE Transactions on Automation Science. He was the founding editor-in-chief. So he said that one robot is robotics and many robots is automation. So, uh, so what we see here, like any of these manufacturing systems, you will have many robotic systems working along with one another. But what actually this is like an implementation of an automation system. And then what is the unique aspect of automation system? I have to achieve a final goal and I don't need to mimic a human or not. So I will have a suitable programming system, and then I will have a feedback system consisting of sensors, etc. And then using a particular computation or a control strategy, I will make the system achieve the desired output, even in the presence of disturbance and in the presence of uncertainties in the system. So this is actually talking about nothing other than a control system. So automation systems have the main focus on control systems, and one of the earliest control system was like mm, the speed governor for steam engine. So you had like when the speed goes less, I will be letting more steam, and then there will be like a mechanism governor which allows more steam to come in. When the speed increases, I need to reduce the amount of steam using the governor system. So earlier we had a mechanical control system, and this was an implementation of that control system. Now from automation, we are moving to another phase. From automation, we are moving to the another aspect called autonomy. So now I want to ask the audience, so what are common among all these cars? These are cars which we can buy in India. There is something which is common with all these cars.
They all have high-tech features like AI-based features, which is mostly like auto driving and auto moving sensors in it. Most of the latest sensor which we are using in robotics and other usages.
Yeah. All the cars, even other cars have those kind of possibilities. So what I'm looking for is something else. Uh, every cars have it. These cars have slightly
This
more
these cars have ADAS in it, like the
Yes,
level
yes,
of ADAS.
yeah. So what is the full form of ADAS?
Autonomous driving assistive system.
Yeah. So there is a driver assisting system for all these cars. So that means the within a limited in a more controlled kind of environment, I can like take my hands off my steering, etc. So this is called as actually, when you come look at it, SAE has 6 levels of driving automation. So it is called as, I will highlight this. This is called as driving automation. So the first 3 levels, the driver is in mostly in control, but the driver will get some assist, some information, and then driver will also have some possibility of like getting help regarding changing the direction of the vehicle, or sometimes changing the direction and changing the speed of the vehicle. uh, but these are 0 to 2 level of automation in driving. There are 3 more levels. In the 3 levels, uh, like mostly it may be possible that you are not driving when these automated driving features are engaged, even if you are seated in the driver's seat. And in only level 3, when the feature request, you must drive. Otherwise, the car itself should be making all the decisions regarding what to do: acceleration, deceleration, stopping, changing lane, everything. And uh, these are automated driving features, and the highest level which is possible is level 5. So it can drive the vehicle in all possible conditions. uh, there is no restrictions, but whereas SAE level 4, this is the place, some like implementations are there in US, and some implementations demonstrations have been done in our country as well. So there are local, we don't have local driverless taxis. Some places will has local driverless taxis. uh, it may not have pedal, steering wheel, etc., which will be present. So this is actually levels of automation. So you are starting with a basic level of automation, and then you are moving to a higher level of automation. So all of this is leading to something called, we are moving from automation to autonomy. So what do you mean by automation? your decision made or actions taken by automated system are based on predefined heuristics. But in autonomy, the system learns and it adapts to dynamic environments. So in to some extent, the highest level of automation, that is level 5, uh, will depend upon uh, environments that is already trained. For example, if you're looking at level 4, you are looking at local driverless taxi, that is for a particular place which is proper, where the structure is good, there you are going to have a driverless taxi. But if you take it and drop it, leave it in a new place based on the information or like the learning that it has done, if it is able to work without human intervention, then that can be considered as autonomous kind of system. So people have been using autonomy for driving systems, but it is said that autonomous driving is beyond the level 5, because if you are put in a new environment where the training has not happened, where the data has not been recorded in a new way, still the system should be able to function. So this is based upon this particular paper, Level of Automation and Autonomy, by this particular author. And even if the environment changes, autonomous system evolves and improves its behavior over time, and the autonomous system is able to handle more complex and unpredictable situations. And one of the major important aspect in any system is like safety and functionality. Both have to be up to the mark. So I am talking about all this. The robotic systems, once people said it is like a very mechanical kind of system which does not react to a particular situation, then we came into automation, then we came into autonomy. So what is one of the reason why this is possible is these aspects of sensors which are present in the system. So if you have a automated driving kind of system, you have multiple sensors. You have lidars, we have radars, we have cameras, etc. So you will have multiple cameras around, and those cameras can be used to allow for some automated driving kind of possibilities. Now I am focusing on this particular one sensor, that is this aspect called computer vision. So wherein like these cameras, data from the camera is used to make decisions and measurements. So what is earlier computer vision was like something like an evolving kind of area. But the last 10 years ago, there were two Nobel Prizes which were given for developments which are related to computer vision. So one of it is on, if somebody can volunteer, can you say what is this first image? So it is connected to Nobel Prize either in physics or chemistry in 2015 to 18 or something. Might be somebody can just make a
Does
try.
rover had a lidar system?
No, no. What I'm
No.
talking about is this image, this in yellow color. Can you make a guess what it is about?
It's a like a laser system which analyzes the heat and the circulation with a UV rays or something, like a sensor which is used latestly in Volvo company's cars, which has a certain amount of limitations, but it has a high infrared sensors via which we can identify the things which is in front of us in an automated way, in a clear cut.
No, no. So it's not related to autonomous driving.
Sir, is it like a thermal vision sensor or like device?
It's not a thermal vision system also. So this was for a microscopy. So what I am making a point here. So this is a microscopy image, and the illumination is called as like a particular dark field kind of illumination. And then using this microscopy technique as well as the computer vision image processing techniques, it was possible to which take images of very small objects, very small features of objects. So some of the features are zero point 0.1 micrometer, etc. And if that is the case, what is the next image? On the right side of that. So one was for one got Nobel Prize. The work, one of this work got Nobel Prize for chemistry, and then for physics the consecutive years. I think 14, 15 or 15, 16 or something like that. So I think if you go to this nobelprize.org, you'll be able to see all these stories about the Nobel Prize. So this is about protein structure, and the structure also was determined using computer vision techniques. So what I'm saying is image processing was something like a kind of an engineering kind of application. Then it has been implemented like used in a large scale even in science, physics, etc. And then even Nobel Prize have been granted based on the work on computer vision kind of techniques. So then the last image, what is this image? What is the uniqueness of this image on the rightmost? Can somebody volunteer? What it is showing a map. Which map is being shown?
So it's a satellite. Uh, it's an image which has been taken by satellite cameras.
Yeah, it is an image that has been taken by a camera, but it's not in satellite. Ah, yeah, it can. It is a satellite, but do you know where that satellite was?
Like above India, I think, in between Asia and African continent.
Uh, so it was like a satellite of the Earth or some other planet. Like was it orbiting Earth or some other planet?
Obviously, it's Earth.
Planet Earth.
So as per ISRO, this is the image that has been obtained by our Mangalyaan mission. So our Mangalyaan mission had a camera. Using that camera, an image has been captured of Indian subcontinent. So we can say that this would be the farthest we could have like looked at India using our own ISRO's indigenous technologies. So I also use this kind of image to say that when we look at the photo of India, you don't see like any people or any state or anybody speaking a particular language or any difference. You will see it's like a united kind of place. And then the whole world is also connected to one another. So this like on a philosophical note, when we look at situations from a distance, like many of the differences and all those things vanish. So this would have been a way of like retrospecting upon like what we are as a country, as a people like of India. So something which is like thought provoking, but then it is like a result of a technological advantage. So actually, I am making a point that computer vision is being applied from microscopy for a micro scale kind of application to like a extraplanetary exploration. This the bottom what you see is Mars Explorer. So it has a camera at the top. So so if you go to this the NASA, this is from the European Space Agency. So there is this ExoMars rover. In that you have these like camera-based systems. So the cameras are on your road, are used for microscopy. It is used for looking at yourself from far away. It is also used for analyzing uh, information on other planets even. So the kind of scale across which you are using this information is very large. Now, from there, I'm moving to this aspect of robotic vision. So if a robotic system, so I had shown the image of robots, then I talked about some introduction about, I gave some introduction about computer vision system. If the robots are guided by measurements from cameras, we can say it is a robotic system. So you have a visual sensing system, which is like a camera, and then a mechanical actuator. Like these are wheels, which are mechanical actuator and which is connected to a computer. What is this? Rightmost, you have an image. Does somebody have an idea what is this image about? So this was the most earliest application of computer vision for robotics, which is documented.
Sir, what this robot called? Like what's his
Yes.
name?
Yeah, you can say the name and what was unique about this particular robot. So let me other than if you are spending a lot of time, you'll lose a lot of time. So this robot is called a Shaky. So Shaky was one of the first mobile robot which had a camera system attached to it. And then one of the earliest demonstration of computer vision techniques was to navigate this Shaky using uh, the camera mounted on the particular mobile robot. And this was given, initially it was thought that computer vision is a very simple kind of topic which can be solved in 2 3 weeks. So one of the professors who worked on it gave a internship to one of the students. So the first work related to computer vision was done as an internship, but still, even after so many decades, like many of these aspects of computer vision is still a matter of interest and matter of research. Now, while we come to robotic vision, we actually look at human biological mimicry. So we can say that the camera mimics the human eye, the computer mimics the human brain, your actuators and systems mimic the human limbs, etc. Now the challenges for robotic vision system is like uh, some of the benchmarks is to achieve human biological capability. So today, if you build a robotic system, always you will compare it with the capability of humans. And therefore, normally it will involve the study of humans and living organisms. And what do you do after the study? You will try to build a mimicry of the system. And what is the end result? You are able to do repeated tasks for longer time without tiring. You are able to increase precision of a particular task. And then you are able to protect humans from dangerous and less pleasing environments. So that brings me to some very basic foundational introduction about robotic vision systems. So now I am taking you on some practical applications where computer vision has been applied as part of my research. So one of the application which we worked on is these are called as uh, those when you manufacture textiles, you will have cotton which is used to make uh, threads, and then there is something called this. These are kind of wheels on which these are rings on which a particular wheel will move, and this component is like a component which is manufactured in a very large scale, and then after manufacturing, uh, a human had to inspect this particular system, and the industry had a requirement that you should have a automated system to detect the defect and then classify the defect. So therefore, based upon the requirement of the industry, there were like many defects. This is one kind of defect, this is another kind of defect. This is another kind of defect. This is another kind of defect. Then again, fifth and sixth kind of defects, blisters built up, etc. So using a camera-based setup, so earlier our team, like myself and others, had developed a system to do to detect these defects in the image. So input is an image from a camera, and output is what kind of class of defect is actually produced. So the requirement of the industry was to say that instead of humans, I need a computer vision kind of system which inspects and make decisions regarding what is the defect and what is the category of defects. So using some image fusion techniques and some machine learning approaches, the type of defect, that is, this is one type of defect, yellow is another kind of defect, blue is another kind of defects. So the types of defects could be identified. So some of this, a part of this work has been published as a journal article. Now the problem in such industrial kind of system is that you will not have enough of defective components to produce the particular data set. So if you want to build a machine learning kind of model, you need a large data set to train your machine learning model. So there was another problem which was given by another industry, which is like an international industry. Like some of these small uh, uh, defects in this particular pins. This is a longer pin. So in this particular region, there is a defect, and this had to be detected. But now, if I'm using any of these standard deep learning kind of techniques, you need a large data set to train the model. So therefore, instead of actually getting images from the defective images, a generative method has been used. There is a method called GANs, or variations of GANs, that has been used to generate images. Earlier, we were using exact images of the exact environment. That instead of that, if you are able to create these data sets using generative methods, you can use it to train our models much easier, especially deep learning kind of models. So some publication has come on this work. And another work which we are involved in is in robotic bin picking and assembly. So you have nuclear reactors, and nuclear reactors have these pellets, and these pellets are manipulated by humans, and then it has to be arranged in this particular tubes, and then this is sent to the reactors. And humans have like radiation measurement systems. So these are uranium pellets. So if somebody handles these pellets, those people will get exposed to radiation, and therefore once the radiation levels are met, then the person cannot handle it. So we had built a setup at IIT Delhi to pick up this. So this project was given by BRC Mumbai. So if somebody has gone to BRC Mumbai, they have this application. So you have a bin, and you have a camera and a 2D scanner. Using the camera and 2D scanner, you scan the region, and then you detect the position and then pick it up. So this robot is actually picking up and then arranging these pellets. These are not actually nuclear fuel pellets. These are actually samples of nuclear fuel pellets. And this uses two sensors mainly, that is 2D sensor, laser scanner, 2D laser scanner, and a camera to detect and then pick up these objects and assemble it. So using the camera information, I can also check whether there is some, when I pick up, if there is some disturbance that has happened. For example, somebody disturbs the environment. I take an image, and then I find out the undisturbed area, and then I can pick up objects from the undisturbed area. This also has been published and demonstrated and then published in international this conference called IROS. So this had this industrial robot, camera, laser scanner, and a vacuum gripper, and two types of end effector, that is vacuum gripper and parallel jaw grippers, to scan, and then like the sensors help us to scan, and the grippers help us to manipulate the object. And this is the laser scan line which is falling on the bin. So this is actually called as a bin picking application. And normally earlier this was done using like human operators. And I don't know the current status at BRC. Perhaps there is some progress in that. Another project on the same was like these pellets had to be picked up and had to be assembled in a uh, uh, tube. So you come close to the tube using visual data, and then control the force, and then you check for the location where the assembly can happen, and then you assemble the the pellets. And there are numerous other applications. This is like a touch, like using camera, a touch sensitive screen, like just like a normal screen, blackboard. This screen, projected screen, can be converted to like interactive screen using the camera which is here. And then you can interact with the board using like even without touching, with some gestures we can write on the board. So this was done as part of a computer vision project while I was teaching computer vision for one of the classes in my former university. So this is one application. And another is one system which we have developed for teaching alphabets to children. So here we don't have a camera, but we have a 2D sensor, LiDAR sensor. Using that, a normal screen is converted to, normal surface is converted to an interactive kind of surface. And you can interact with it. And then this is actually used for teaching alphabets to children. And another of it is like a drone mounted during the COVID system. Again, while I was teaching computer vision, we had this project. So one of the students developed this. You have a camera on the drone. When the drone flies, the camera detects the image and then says whether the person is masked or unmasked. So the person behind is unmasked. The person who is in the front is masked. So I am also not masked. So I am uh, annotated as unmasked. So this has been demonstrated by the student also for some competitions, etc. So I think I will quickly go through the other applications also, 5 more minutes, and then wind up because we started 5 minutes later. Is that okay?
Yes, sir.
Yeah.
Yes,
So
sir. Yes.
Yes, sir.
so this is like a system for localization of drones. So you have a drone, and then the drone flies away and has to localize so that it can be charged. So this localization was done using like some fiducial markers. So we worked on a computer vision based technique, like a visual servoing kind of technique, to localize the drone and land, so that when it lands accurately, then uh, so this is like a like image servoing based approach. This is done in simulation mostly. You have a marker. The system first localizes itself with respect to the marker, and then it will localize with respect to the second marker. Yeah. Are there any queries?
No, sir.
So
Please continue.
yes, yes. So this simulation has been done in Gazebo using ROS-based system, and currently we also worked on something like a concept called robotic assembly using multiple capabilities. So this is like a work which is in progress. We call it a resilient assembly. You pick up the object and then do assembly using vision as well as force data. And also there is also possibility that you can also use a teleoperation kind of system using a haptic device for picking up and then doing assembly. So this is in this you have a camera at the end, and then robotic system actually can sense the force which is experienced at the end. So this is the force at the bottom left side, which is used to send which is sensed at the sensors, and then you come close to the hole, and then on the top left you have the camera view, and then you assemble it along with the direction of the hole. And then here the difference between earlier approach, this is like a continuous visual surveying kind of approach. So that means I am continuously capturing data from the camera and then doing the assembly. And the robot, if I don't have continuous feedback from the camera, because of the clearance between the peg and the hole, I will not be able to do assembly. And then the same can be done using a haptic device. So haptic device can be used to pick up and assemble. So this you will see that at a later stage when the robot comes closer to the hole, uh, like he will take over and then do the assembly. Yeah, at this stage he picks up the haptic device, and then using the feedback in the system, he does the assembly, and he is able to successfully do the assembly. So this we were proposing as, like, we are not yet published it. We are calling it as a resilient assembly system with multiple possibilities like autonomous, teleoperate, shared control, etc. And it's not published, so we will not be able to discuss much on it. And then this is an ongoing work which we are doing at IIT Madras. You have like a very heavy duty two robots, and these robots are assembled together so that you can do a sheet metal forming application. So one robot will push from one side, the other robot will push from the other side. So using this, you can form components. You can where do you use sheet metal forming? Normally for making the bodies of cars and automobiles and many day-to-day items. So initially there was like a large error between uh, uh, the both robots. Therefore, it was not possible to do collaborative or coordinated kind of forming. So we are now working on like a camera base. You have a camera, and then you have some markers using that how to do calibration. So I have a few publication in these areas in some of the journals. So we are going to extend it to coordinated robot calibration as well. So this brings me to the end of this discussion. In summary, we looked at robots, definition and aspects of industrial robots. We looked at automation, important aspects, and then from how automation to autonomy is coming in. The moment you bring in automation and autonomy, the sensor information is important. Therefore, computer vision aspects become important. And we looked at some case studies and some ongoing research. So as we conclude the first session, uh, so visual sensing for robotics and automation has applications, and it has a large potential to influence our lives and ongoing research activities. So I think with this, I can wind up the first session. So many of these activities, some of them were funded by BRNS Mumbai. Some of the activities were at IIT Delhi, Innopolis University, Russia, IIT Madras, IIT Jodhpur. Then it has been supported by Russian Science Fund, and this is one of the sunsets in the former university where I was working. So this is the end of the first session. Second session we'll again meet together, and I will be discussing more on basics of computer vision.
Yes, sir. Thank you. Thank you for your valuable session. So, all the participant, we will take a break for 10 minutes, and we will start the second session exactly at 3:15. Is it okay, sir?
Okay, okay, you can
Yes.
join.
Yes.
Yeah, dear participants, do not leave the session. So we have another session with the same faculty. So he'll be continuing the same. Okay. So please don't leave the session. Rejoin at
Yes.
3:15.
Meanwhile, I have just posted a link in the chat box for the today's feedback. after the session. So all are requested to give your valuable feedback after both second session when the session is going to be finished. Hello, welcome back for the second session of this FDP. So, Rabi sir, shall we start? Your mic is mute, sir. Your mic is mute.
Oh, sorry. If we are ready, we can start right away.
Yes, sir. Yes, sir. The session. So, we will start. Thank you, sir. Thank you.
So, hope you had a quick break, and uh, small recollection of what we did was we found that robotic systems and sensors, especially vision, is something very important. So, the current mm, session, I will focus on computer vision techniques, starting from some basic concepts of computer vision. I don't know how far you will be able to go because uh, normally we teach it as like a 39 lecture course, computer vision, while we normally teach. So I am only trying to give a small purview of this basic computer vision aspects. While applying it to robotic systems, it might take like uh, it might not be possible to cover exactly those aspects, but in the first session we already heard about where it can be applied. So let us start with so I think you are able to see my screen. Can somebody, like, I
Yes, sir.
have
Yes, sir.
shared the screen? Okay, so my slides are visible. So
Yes, sir.
I
Yes.
the session I am naming it as introduction to vision, and some basic concepts I will cover first. My source of this material is a book by Selesky, Computer Vision, Algorithms and Application. It's freely available online, so you can freely download it and use it as well. And then some adaptations, slight adaptations, I would have done as per the requirements. So we'll first start with looking at some geometrical primitives and transformations. Uh, Imagine I have a 2D point. The 2D point, uh, it will have two coordinates, that is x, y, and then I define a vector, that is x is equal to vector with two components, that is x and y component. I write it as in this particular form. So all whenever I write it in text, I write it as xy and then transform so that I can write it in the text as I written, but both are the same. Now these 2D coordinates can be represented as homogeneous coordinates. So what is homogeneous coordinate? You add an additional coordinate, that is w tilde, at the bottom of a and that is the as the third dimension, third coordinate of a component of the particular vector, and then this x tilde, the new vector, will have the components as x tilde, y tilde, and w tilde. So then it is supposed to be like a element of like the 2D projective space. So that is defined as P2, which is shown here. Now uh, there is a correspondence between x tilde, y tilde, and w tilde and xy, that is a 2D point, which will come close, which will come like in we'll discuss in a small while. So if it is a homogeneous coordinate, if I'm multiplying this x tilde by another constant number, even that vector is considered as equivalent to the original x tilde that has been there. And then this projective space will not have this particular component, that is 0 0 0 component. So if I remove 0 0, that is the 0 0 0, that is the origin from R3, the three-dimensional real space, then I will get the 2D projective space. Now, how to convert back from x tilde to x? So you have the homogeneous vector, and then I want to convert it to inhomogeneous vector, that is x. So how do you convert it? You multiply all the elements, that is x tilde, y tilde, and w tilde by w tilde, and then you will get xy1 equal to x tilde. And this xy1 is same as this particular vector, that is x. So this xy1 is called as an augmented vector, where along with xy coordinate I will also add 1. So why we are actually interested in this homogeneous coordinate system is that in a real coordinate system, we are normally saying that our point at, like, if a point is at infinite kind of location, infinite kind of distance, we say that its location is not defined. However, in an image, even if the object is at infinity, you will have a representation for that particular object's coordinates, at the position of that particular coordinates in image coordinates. So that is why homogeneous coordinate system is used. And what are those points which are at infinity? Those points are w tilde is equal to 0. So for any coordinate, if I write the last coordinate, like homogeneous coordinate, last coordinate as 0, that corresponds to points which are at infinity. So this is about homogeneous and inhomogeneous coordinates and augmented vectors. Now, there are some aspects called as geometric primitives and transformations. So if I have an image of this particular type, so if I do some transformation, just like the word transform, it can be changed if I do a translation. So if I imagine that the let me go to the next. So imagine my input image coordinates are something like this, and then imagine the initial image was something like this. After translation, the image will be at a different location, but our initial uh, the image, like this small part would be there, like which defines it, but then imagine that this is like a big canvas of the image, black colored, and then initial image which was at the bottom of the canvas, if I shift it, then it will go to another location of the particular canvas. So this called as translation transformation. This you normally do it in or any of these softwares, that is Photoshop or GIMP or something like that. And coming back, so this is translation. Then I can have a Euclidean transform. So where I do translation and then rotate the image as well. Then I can have another transform which is called as similarity transform. Are there any queries? Okay, if there are no queries, I will continue. So in similarity transform, I do translation and rotation. Along with that, I do a scaling also. And then there is a transform called affine transform, where the image will get, the shape will get twisted and changed in some way. And then there is something called projective transform. So these are different transforms that are present. And then if I want a translation, so I can multiply my in the current, like what is actually getting transformed, the coordinate system or a particular vector which is represented in the coordinate system gets transformed into another coordinate system. So I can use a particular matrix to transform a particular point in the image to a new point after doing the transformation, that is either translation, Euclidean transform, similarity transform, affine transform, projective transform. How do I do it? So imagine that I have my vector p. P is actually present. It is some point here, and now due to the translation, that same point gets transformed to another location. So that is transformed by so this p becomes, will get changed as p dash. And now if I want to obtain the coordinate of p dash, so I have to multiply p by a transformation matrix, then I will get p dash. And then p, it has to be an augmented vector, so it should be like of the form p dash. And then what I am getting here is p dash. So p bar will be of the form x y 1, and then my, if it is translation, if it is only translation, so I will have like the component of this. This is a matrix. This is actually a 2 cross 3 matrix. So I will have 1 0 tx 0 1 ty 0 0 1. Then if I multiply it, I will get you will be able to find that it is of the form x plus tx, y plus ty, and so if imagine this is, sorry, this element I am not considering, last row is not I am considering. So I will have p dash as x plus tx, y plus ty. So which is shown here. And the same thing can be done for rotation as well. So in rotation, what happens is this matrix, this T 2 cross 3 matrix will become like, I will have a rotation vector, rotation matrix, which can rotate a which will have the effect of rotation of the this thing, and then you will have a translation part. This Tx Ty is the translation. So the translation, this particular origin gets translated by tx and ty. And what is rotation? Imagine that my system is transformed here. I will have this as tx uh, ty, and then that this coordinate system is rotated with respect to, this becomes x dash and y dash, and this is rotated with respect to existing earlier coordinate system. So that rotation is represented by rotation matrix. So this 2 cross 3 matrix would be 2 cross 3 using a 2 cross 2 rotation rotation matrix, and a 2 cross 1 translation vector, and that is used to convert p bar into, p bar is converted to p dash by p bar multiplied by t, giving you p dash. So same thing can be uh, like extrapolated to similarity transform. Only thing is this rotation matrix, 2 into 2 rotation matrix will be multiplied by an element s, which will give a similarity. So it will either scale it or then string the image. So similar to what we showed here. So it increases the size or decreases size of the image. Then there is a so this matrix is 2 cross 3, earlier also 2 cross 3, 2 cross 3. Then there is a transform called affine transform. Now what one information about any object in the image is always uh, mm, preserved even after transformation. If it is translation, orientation, that is, if I have like image, so all the image like angles would be with the same as before uh, with respect to my original coordinate system. And then if my lengths are preserved, my the lengths of the object which is present in the image will be same in the initial as well as final. If the angles are preserved, that means the angles, that is 90 degree, 90 degree, and will be preserved. But in affine transform, the angles can be changed to any kind of, it will get changed into a different kind of angles. And then in projective, the transformation matrix is used, a 3x3 transformation matrix is used, where straight lines remain straight lines in the beginning and the end. Like initially also this line was straight, and after transformation also it is straight. These lines are straight. So only straight line information is safe. Uh, so while I look at translation, my lengths, angles, parallelism, straight lines, and orientation are maintained. When I look at Euclidean, lengths, angles, parallelism, and straight lines are maintained. When I'm looking at similarity, angles, parallelism, straight lines are maintained. And then when I look at affine, parallelism and straight lines are maintained. And then when I look at projective, only straight lines will remain straight. All other information will get changed. So this is like some transformation operations which normally gets applied on the image, and then it gets changed to something else. Like the image would get changed to a different kind of image. Now the same, this was for transforming a 2D coordinate. So same kind of transformations exist for 3D coordinates also. So if it is 3D coordinate, the difference is I will have, like, instead of 2 cross mm, 3, I will have 3 cross 4 size transformation matrix, 3 cross 4, and then similarity also 3 cross 4, affine also 3 cross 4. And the projective transformation, you will have an additional row, and then it becomes 4 cross 4 transformations. And in projective transform, or this is projective transforms, it can be, it can also be called as perspective transform or homography or collineation. So if I do this multiplication, what I'm getting is a homogeneous coordinate. So that means I have to divide all the elements by the last element to obtain the actual coordinates of which is obtained after the transformation. Now, in all this, I talked about a rotation matrix. So what are the rotation matrices in 2D plane? Rotation matrix is corresponding to rotation about only one particular axis. So that would be, so in 2D I had written P is equal to RT, and then my rotation matrix is always rotating. Imagine my X and Y plane are on the 2D plane, and Z axis is perpendicular to it. So it would be of the form of uh, cos theta minus sin theta, cos theta, if it is representing rotation of 30 theta degree with respect to Z axis. Now, if it is 3D, so I can have like rotation about not just Z, but I can also have rotation about X, uh, for example, alpha, about y axis by beta, etc. So those rotations, so it will become like your rotation matrix uh, represent orientation of a coordinate frame after transformation uh, using the direction cosines of the axis of the coordinate. So if you want to understand what these coordinate systems are, so if I have like initial coordinate system, that is x0, y0, and something like z0, then I have a new coordinate system which is like x0, x1, y1, and z1. So what does this rotation matrix that relate, that is from here to here, if there is a rotation matrix, what does it represent? The rotation matrix, first column would be the direction cosine of x1. So direction cosine of x1, and then the second column would be direction cosine of y1, and third column would be direction cosine of z1. And then if I am making a rotation about only z0 axis, so this direction cosine of z0 and z1 would be same. So then I will have x1 y1 and then 0 0 1, which is the direction cosine of uh, initial value, that is initial coordinate system 1 itself. But then these two elements, these two into two matrix elements, the sub matrix will be different. This rotation matrix also has some properties, so I will not go into the depth of it. So if I am rotating about z, you will get this particular rotation matrix. And then if I this is normally taught in robotics course, if you have done it. So if I do rotation about z, and then the new uh, uh, for example, if I do rotation about x-axis, and then the new y-axis which is formed with respect to the do rotation about that y-axis by beta, and then with respect to the new z-axis I do rotation by gamma. So then overall rotation matrix is multiplication of all these individual rotation matrices. So for further information, you would have to refer to any of these robotics books where you learn about forward kinematics. So all of this I am teaching because while image is formed, you have a point that is PC or PC in the camera coordinate system, and then it is represented as like in a world coordinate system, it is represented as PW. So if my PW has to be converted to an image coordinate, for example, I have a camera and then it is image like taking a photo of PC or PW. So I can uh, find out what image that at what location in the image that PC or PW will be seen. So that place where I am finding that particular point is xs tilde, which is like homogeneous coordinate of the point in the image. So imagine this is the image. This image, this point is the place where this point PC is seen in the image. So now xs tilde is my homogeneous coordinate which represent that particular point. So that is related to PW bar, that is the coordinate in the world coordinate system using this matrix, that is K into RT. So K is a so in my expression what I had used is xs tilde is equal to K into, this is R is a rotation matrix, this is like a rotation matrix, and then you have a translation vector, both are combined into one, and then I multiplied by PW bar. So if you recollect what we did earlier, this transformation is actually a Euclidean transform because it has R and T which is present, and the whole thing is transformed by this K matrix. What is there inside this K matrix? In K matrix, I have fx 0, cx 0, fi, cy, and 0 0 1. So I PW bar is converted to PW dash, or even I can say it is like converted to PC. So PC is the coordinate of the camera of the 3D point in the camera coordinate system. Then this PC is undergoes a projective transform. so that I will get XS tilde. So if I have something like XC, YC, ZC, and then I multiply it by Fx 0, Cx 0, Fy, Cy 0, 0, 1. I will get this as Fx into Xc plus uh, uh, X. Sorry, this should be Cx plus Cx. Fy into Yc plus Cy. And then I will have Zc. And then XS tilde, if I want to convert it into uh, XS bar, so I just take ZC outside, so I can multiply Fx into Xc Cx by Zc, Fi into Yc plus Cy by Zc 1. So I will have 3 curves 1. And within this part is my 2D coordinate of the the camera where the point has formed in the camera. So this is like the standard expression for image formation. So this matrix which we have here is actually called as like a intrinsic matrix, and this matrix which consists of R and T is actually Euclidean transform. It is called as extrinsic matrix, and in this intrinsic matrix is related to what all things? It is a property of the camera. Uh, but extrinsic matrix is how I orient the camera with respect to my world coordinate system. But intrinsic matrix is dependent upon the lens, the sensors which is there in the camera. Like you will have either CCD or CMOS sensors, and you will have these many pixels, and there will be a particular size of these pixels. So those will aspects will determine F, this alpha into S F, as well as Cx, Cy, and mostly in the current cameras, this S component would be equal to 0. So, so in short, if you have a 3D point that is PW, you convert to augmented vector, multiply it by K RT, then I will be able to get a homogeneous vector XS tilde, which represent the coordinate of the image that was formed. So what we discussed till now is geometrical image formation. So it's called as geometrical information because depending upon the geometry, that is the 3D coordinate PW bar, I determine where the image will get formed. But there is also one aspect. This only tells where that point will be visible in the image. But there is also one another aspect. How much would be the color or like the brightness or the how much dark that particular point will look like, that is determined using photometric image formation. So earlier what you are looking at using the 3D geometry, that is the rotation, translation, as well as the intrinsic matrix, I determine the geometry, I use it to determine the position of the 2D coordinate. Next, I determine the source of light, how the light is getting reflected, etc. To determine how bright that point will look like. So in any standard image formation systems, you will have an input in her input light from a light source that will fall on a particular surface, and then it will scatter light in different directions. And then with respect to the normal, and then one of this scattered light passes through the optics of the camera and falls on the sensor. And then you determine that at that particular location, this particular point image is formed at that particular location. Now, wherever what is the source of the light and on what surface the light has uh, fell, that will determine the brightness of the image, even the color of the particular point. So in a digital camera, basic structure is like you have like the light from a source. It goes through the optics. There will be some lens. Then there will be an aperture. Aperture controls the amount of light that goes in. There will be shutter to control like the duration for which the light is allowed to fall. And then This is the camera physical body. So normally if you have any camera like DSLR or something, the physical body, if you just remove the lens, that is a physical body. Like that lens has like all these aspects, optics, aperture, shutter, which is all incorporated into it. And then the camera part, like the backside, the other part after removing the lens is the sensor, has a sensor chip, etc. So it has a sensor there. Actually there is some gain that is being applied, then there is an analog to digital converter, and then you will get output image from that body, and then that gets stored in your memory stick or something. And if it is connected to, yeah, through USB camera, as my camera is connected at this particular point, then it gets processed further, some other process is done, so it will not be stored as a raw image. Then the output image or like the video undergoes some image processing or signal processing steps, and then finally the outcome can be something like a JPEG kind of image. Uh, so in the digital camera, the lights starts from one or more light sources. It reflects off one or more surfaces in the world, and then pass through the optics, and then it reaches the image sensor. So in the image sensor, and there will be an active sensing region, and then depending for the duration of the exposure, normally the shutter speed, if it is very fast, then less light will fall in. If it is slow, then there will be a lot of light that falls in. Then the signal processing happens for that particular information. So the light falls on the sensor, active sensor area. If it is a CCD, there is a process called bucketing. So all those charges gets formed due to the light. Like this is like a photosensitive kind of sensor. So charges get formed, and that charges are transferred from one CCD sensor to another, and then it is converted to a voltage, and then that voltage is read out as like the information or the brightness of that particular pixel. But in CMOS, you have a different kind of structure. You have very small like sensors, and each sensor is connected to independently. It does not pass through other kind of sensors. It is independently connected to a like a central kind of system, where all the charges gets converted to voltage and then get passed. So some of the sensor will look something like this. You will have a photo diode and then multiple other components which will be present. So you have two options, either CCD or CMOS. CCD are supposed to have good quality of images, and then the only difference is that photons are accumulated in each active wall, and then it is transformed one by one across the different the wells, or like different uh, sensors, and then it gets converted to a particular signal, and then that is recorded or displayed or anything. But in CMOS, directly it gets like the image data gets uh, uh, converted as a sensory information, and then directly it is sent to that central uh, 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 location from where the sensor signal is captured. So some other aspects of the physical digital camera is shutter speed, sampling pitch, fill factor, chip size, analog gain, sensor noise, ADC resolution, newer sensors, etc. So these are all some important aspects of digital camera. And then as you start looking at buying a camera, or like you start to analyze the camera which you have, you will find all these aspects are relevant. So most likely when you buy a professional camera, you would be able to look at all this. Also, if you are buying kind of an industrial kind of camera, you might be able to get access to it. So the digital camera also gives output in terms of colors. So basic colors are either red, green, blue kind of colors, or combination of red, green, that is uh, like the cyan, magenta, and yellow kind of colors. So you can represent either as RGB or CMY kind of colors, and these choices are normally uh, decided by the way the particular application which you are going to use that particular uh, uh, output from the camera, that is image. So RGB image will look like this. Individual channels, red, green, and blue, will look something like this when we plot it as grayscale images. So if I want to have a color image will have three different images corresponding to red, green, and blue, and then that is shown in here. For example, one particular color will not be so dominant, whereas another color will be dominant in a particular region, that you will be able to see. For example, blue is dominant in this particular image, this region. And there are other smaller, better, or like alternate representations. Instead of capital RGB, you can have like another representation which is represented using RGB, small RGB. Then there is LAB representation, then there is HSV representation. For different application, any of these kind of representations are used. Now in a digital camera, how is color captured? So you have like a sensor array in the camera, and then one of the sensor is having like a filter corresponding to green, and then you can see near that you have other sensors with other kind of filters. The next one is with R, and then after that G again R, then after that you have B, G, B, G, then G, R, G, R, and then BG, BG. So the number of uh, green color regions are more. So what does that mean? Green color, there are more pixels capturing green information, and then less number of pixels capturing the red information. So mainly the brightness may most likely be determined by the green colored green, the pixels with green filter. So the number of pixels also, like 1 2 3 4 5 6 7 8. Here it is 8. Red will only be 4, blue also will be 4. So this this says that the camera, this particular camera would be double, like having double number of pixels, and will be more sensitive to green color. uh, Now imagine that we like had a camera, we took an image. So image, from the image, you know, the 2D 3D coordinate, 2D coordinate of a particular point, and then you know the brightness. So any image output would be looking something like this. Now, if you get an input like this, you may have to do some transformations on those, that particular image. So what kind of transformations will you do? Like you may change its brightness, you may convert to grayscale kind of image. You may change its other properties of the image, etc. You may change the shape of it. So image processing process the image and convert it into form suitable for further analysis. So the examples are exposure correction, color balancing. You may have to reduce the image noise. You may have to increase the sharpness. You may straighten the image by rotating the image, etc. So now what kind of image processing you have to do will depend upon the application that you are targeting. So if a particular application requires a specific kind of processing, then uh, that kind of application will have to be applied. Uh, so what has happened while we do image processing? The image processing operators map pixel values from one image to another. So it takes a pixel from here, and then, so pixel means the location of that particular point in the image. So the pixel aspect comes from like the sensors. So if you have multiple sensors, you will have multiple information from each sensor. So each sensor will give me one pixel information, and then it would be of the form, if it is like a 8-bit kind of image, you will have information from 0 to 255. 255 will be the brightest point, and 0 would be the minimum value for the particular point. So image processing is example of point operator or point process. So it takes each pixel and then converts it, manipulates it into some other like value for the grayscale of the image. Now there are point operators and neighborhood, uh, that is area based operators. So in uh, area based operator, we are looking at all the pixel values near that particular pixel to determine what would be the current value of the that particular pixel. And then now if you can have multiple like operators acting on the image one after the other, it is a common thing that you'll first apply one particular filter, then after that another kind of filter. Those multiple filters will either improve one feature or like change the effect of one another kind of feature. So in image processing, the most common like approach will be to use a point operator. So the operation is also called as point process. So each output pixel's value depends only on the corresponding input pixel value. Global connected information or parameters will not play any part. For example, brightness and contrast adjustments, color correction and transformations are examples of such a point process. Now, now point process, how it is normally represented is like in the image, you have something like a coordinate that is g1 of xy. So if I do point operation or image processing operation, so I will apply f of g1 g1 xy. Uh, so this will be equal, like the transformation, the point operator will transform that g1 xy uh, by applying function f over it and then add a constant value, uh, something like beta, and that would be stored in the new location. So from here to new location, the image gets changed and then the new base gets formed. So it is of this form, that is uh, g of x is h into f of x. Input is f of x and then I am applying the point transform, that is h on f of x, and I will get g of x. And then what is x? It is a 2D coordinate. That is, x is like along the row, what would be the number of pixels, along the column number of pixels, and then g of ig will be given as h of f of ig. And most commonly, it should be written as g of x is equal to a into f of x plus b. So f of x is ideal case, it is independent of any of the nearby coordinates or points. Uh, so earlier I had said it is a into f of x plus b. Uh, it can also happen a can be a variable as per the location of the pixel from where information is stored, and uh, so here a of x and b of x is varying as per x. Normally it will not be, it will be like a constant. And now if I want to add two images, that is f0 of x and f1 of x, I can use 1 minus alpha into f0 of x plus alpha into f1 of x. And then if you want to do gamma correction, g of x can be equal to f of x raised to 1 by gamma. So there are other kind of transforms which are like color balancing, composting, matching, etc. And then histogram equalization, etc. So these are actually normally taught as image processing algorithms. So next important aspect which in image processing that is present is filtering operation. So you can using filter, you can either blur the image or you can sharpen or smoothen the image also. So so when you're doing filtering, you have input image, something like this. You have a kernel. Using the kernel, you will do filtering, and then the filtered information uh, is like the output image that will be obtained. So earlier it was whatever I was talking about, that is a into f of x, a into f of x plus b is called as point process. But this process is called as neighborhood operator or local operator. So here the idea is I have a kernel. So kernel is something like this, and I have an image something like this, and they are like convolved with one another. When you say convolved, so one way of doing it is like I'll so I have k, that is kernel, and then I have image something like this, k something like this, and on the image I will have multiple image points. So I will first match this kernel at the first location, then I will match, then I will multiply all the elements of k with the elements over which it has been kept, and then add it all together, and then whatever value I am getting, for example, it should be ideally so after doing this uh, so imagine my kernel is 3 cross 3 and this is n cross n. So like I will consider the middle pixel one by one. What I will do is I will put the kernel, overlap the kernel of the other image in the first location, the second location, third location, then fourth location, fifth location, and then sixth location. And then at each location, I will get a new value for the middle point. So those value are the processed information. And while you do this overlapping, you can actually have like continuous shifting of the kernel also. So that this here I am writing that there is no commonality between the kernels. So first three columns are first taken, then next three are taken. That means the first two columns which are there earlier, that is also taken. Then the next three are taken. So one by one, you do that multiplication, sum it. Each element is multiplied by the image coordinate. Then you sum it, then add it and replace the middle pixel by that particular value. So this is important because this is based upon this concept called as convolution. So if you know convolution, CNN, that is convolutional neural network. So this convolution is implemented in this particular fashion, and it is actually a filter. So when you say it is a filter, it extracts some information from the existing environment. And yeah, filter will have multiple effects, and then actually I can do a filtering by if I use a matrix for filtering operation, my computation may increase. So I can actually like separate that 2D kernel into two horizontal and vertical components, and then operate on the original image using like these single vertical and horizontal components. So I can split my K into something like two components, vertical and horizontal, and then that can be uh, combined to do this filter based operation. Now, when you do filtering, the border regions of the image may not give you any output. So your output image size will be smaller. Why? The input image is something like this. So if I overlap the 3 cross 3, imagine that 3 cross 3 is 1, 2, 3, and then 1, 2, 3. So first I'll be overlapping this, and then the region of interest would be in the middle. So I will not be able to get any values for the pixel which is before it, because there is no other existing pixels along with it. Therefore, if I want to consider that as well, that I have to another border or a boundary to the particular system. So those boundaries can be either 0, 0, 0 or something, or can be obtained from like the nearby values. Nearby values can be extended. uh, so that is called as padding. And then if I have different kind of filters, if I have a box filter, uh, it will be of this particular form. So if it is k cross k, all the elements would be 1, and then I will multiply it by 1 by k square. And if it is bilinear filter, it would be of the form 1 2 1 1 2 4 2 1 2 1. And then if it is Gaussian filter, which is a common filter which is used in image processing, so this filter will look like this. This is of the form g raised to minus x square plus y square by 2 sigma square into 1 by 2 pi sigma square. So you can have a Gaussian kernel, You can have a Sobel kernel, and some corner detector can also be used. So each kind of filter will cause the image to change. Because of this filtering, image is looking like this. This filtering, image is looking like this. This filtering, this image will look like this. This something like this, and the last like that. So that is some basic introduction about filtering. And there are ways in which you can split the filter into two parts, vertical and horizontal part, and then uh, do the filtering by using vertical and horizontal parts. And there can be also splitting based on like singular value decomposition. So the last thing which I will talk about, we'll look at few filters. If it is box filter, it will be like this. If I do convolution, my image will get like information. It will be called as a moving average box filter. So at every location in the image, I will add all the elements together divided by the total number of elements in the kernel. Then if I have a piecewise linear 10 function, so the kernel will look like this. And this should be of the form that like the value is increasing from 1 to 2 and then decreasing. So it will be like 1 to 2 and then 1 and then 2 to 4 and 2 and then again 1 to 2 and 1. So that means uh, uh, like uh, it will be the effect, like it will have like two linear kind of splines, and that effect will be there on the image. And if it is a Gaussian kernel is of this particular form, and then it is obtained using Gaussian function, and then the image will get blurred, and then Gaussian function will look something like this. And then if it is Sobel filter, I will have minus on the left hand side, positives on the right hand side, and then my vertical lines, this vertical line, this vertical parts will become more dominant, and it will be visible. And if it is a corner detector, so instead of this kernel is used, so it makes sure that these particular corners are more prominent. So you can use any particular filter which will be enhancing the results which you are looking at. So I will stop at this point. If there is any query, we can discuss any query regarding the first and the second session. So we have covered like some basic about robot vision, and then we started with basics about vision, and we have come till the filtering aspect. So processing, how to capture an image, do some kind of what kind of processing as are done, and then how the image is formed, geometrical image is formed, and then how photometric information is affecting the image formation, etc. If there is any specific queries, some clarification that you require. Am I audible?
Yes, sir. Yes, sir. You're on.
Okay. So I think as per our schedule, like 1 hour is already done. Uh, so what should we do now?
How much you are remain with?
For 1 hour, I plan for this much content only. My content for this hour is complete. First hour, like session, I had also completed. So today's content, what I have planned for, I have completed. Within 2 hours, I can only like plan for this much content.
Okay, okay, sir. Dear participants, if you have any questions, please raise your queries. Anyone with any query? Okay. Thank you, sir. Thank you for the excellent session, sir. We got to know a lot of basics from FDP. Somebody is saying something. Some question in chat box.
Everyone, please give your valuable feedback in the link given in the chat box. Thank you very much, sir, for such a wonderful and informative session. I hope the participants which are attending this FDP, they got to know a lot about basics about the today's session and all. So am I audible, sir?
Yes, yes, yes.
Yes, yes. So if there somebody has a query or something, they can mail me and then get to me also.
Yeah, though if you have any questions regarding today's session, you are requested to uh, write it down on sir's mail ID so that he will reply you back. Or anyone want to ask the question now?
Yeah, I think also we can conclude the session.
So can we conclude the session, sir?
Yeah, yeah, I'm fine. Also, any query regarding the first session also, if somebody has, that also can be discussed. We did
Yes,
not have
yes.
enough time to discuss the first session. That also can be discussed
Yes, sir.
if
Sure, sir.
somebody has.
Sure, sir. So thank you everyone for your presence and all that. Today we will start, tomorrow we will start the third day of this FDP at the scheduled time. Thank you. Thank you very much for your time. Thank you very much, sir, for your valuable time and information. Thank you.
Thank you, and see you. Bye.